and we're good.
It's so strange how few people are here compared to.
I think I've had like only one person sit next to me, and after that, never again.
Nope, I've always had.
I don't know, like, I would get nervous about that. Maybe I'd, like, learn something about myself.
I didn't even say a word.
Yeah.
I know that I'm old and crotchety, so that's why.
If you are, what does that make me?
Most of my friends are
Even
older
older and
Maybe not
crotchety?
crotchety.
I'm pretty crotchety.
Most of my friends are older than me.
We should go around the room and say our
Varying like.
Say what?
Why don't we talk about gases instead? It'll be more fun. Yeah. The older you get, the more gas you give off, right? Isn't that how-
That was okay. That was a good one. That was a good one. That was solid. Or gaseous.
Thanks. All right, partial pressures. Partial pressures is something that everybody kind of gets nervous about because it seems like a special thing, but it's really not. And so we're going to talk about how it's used and how it's really kind of an easy concept. So remember we talked last time about how gases, like you measure them kind of in different ways because they can be difficult to weigh and because the volume doesn't really tell you how much gas you have. Thank you. That's not right there. So we said that you can't really measure, like we don't talk about masses so much when we talk about gas. What did we talk about instead as a good way to measure the amount of gas that you have?
pressure, like ATM.
Well, yeah, there's the pressure, yeah. So atmospheres, things like that. If you look at a gas cylinder, have you ever seen like a gas cylinder? I think there's one up in lab. There's certainly ones over in the instrument room. You'll notice they have gauges on them. And one of those gauges measures like how much gas is left in the cylinder, and that's a measure of pressure. Because you can't necessarily weigh the cylinder to get the mass of what's inside of there, because the cylinder weighs so much in itself. Sometimes that works depending on the type of gas. The volume's always the same because the cylinder always holds the same amount of volume, so you can't use volume. And so pressure is really the measure of how much gas is in there because it's proportional to the number of moles. So when we mix gases, we talk about the amount of each gas through something called partial pressures. So there's this law of partial pressures that states that the total pressure in a mixture of gases in a container is going to be the sum of the pressures of the constituent gases. And sometimes that feels a little weird because we don't think about like gases. So let's say you have a one atmosphere like the air, right? That means that there's going to be different partial pressures from the different parts of air. So nitrogen gas, oxygen gas, water vapor, carbon dioxide are all exerting parts of that pressure, and then you add them all together to get the total pressure, which is one atmosphere. So when we talk about mixes of gases and we talk about how much there is of a certain gas, we can use partial pressures to figure that out. And because of our ideal gas law from last time, we can also substitute these individual ideal gases for moles. So if the total is the sum of the different pressures, that means that the total is also the sum of the individual parts of the gas law, RT over V, and so on. RT and V, notice, don't have 1s and 2s with them because that doesn't change. If you have a cylinder full of gas, that gas is all at the same temperature and it's all in the same volume. So the thing that changes from gas to gas is the pressure and the moles, which are proportional to each other. Right. So in this way, we can use pressure to figure out or to say how much of each type of gas is in there. All right. That also means now that we can think about the pressure and the moles as kind of the same thing. So for instance, there is a proportion between the pressure of, let's say, the first gas, whatever it is, and the total pressure. So let's say, there's the total pressure is 1 atmosphere, and the pressure of what 1 is 0.75 atmospheres or something. So basically 75% is the fraction there. And that's going to be equal to the mole fraction, because all those other things are going to cancel out on both sides. And this thing here has kind of a special name. It's called the mole fraction. And it's given by the, kind of looks like an X in your book, but I think it's actually the Greek letter chi. So we would call that the mole fraction of that one. Of gas 1. So that's simply, that's not like a fancy concept. Mole fraction is literally just like a percentage, but you don't convert it to a percent. It's just the fraction. So it would be something between 0 and 1 for each gas. And then, of course, all the gases in your mixture are going to add up to 1. So the mole fraction and the pressure fraction are kind of interchangeable. In fact, they're equal. And so we can also calculate partial pressures. Rather than going through the gas law, we can also do it total pressure times the mole fraction of 1. So how much, if there's like 75% of 1, then the partial pressure of gas 1 is 75% of the total pressure. So please don't think of this as like some special extra equations that you need to remember. This is just fractions and percentages. Just like any other calculations with fractions and percentages, we're just saying we can do this with pressure the same way we do it with moles. So let's try it. Here's an example question. I'm going to type it here just to make it clear. All right, so a 1 liter mixture of helium, neon, and let me get this thing out of the way. Millimeters of mercury at 298 K. If the partial pressure of helium is 341, whoops. And the partial pressure of neon is 112. What mass of argon is present in the mixture? Okay. You don't need to copy all this down, but let's just grab the important information. We've got a 1 liter mixture, and we have a total pressure, and then the partial pressures of a couple of them are given, and the question is ultimately asking us for the mass. That's what we're going to be answering. All right, so let's look at our container again. Sometimes it's helpful to draw a picture. So let's say that here's our container. It is 1 liter. And it has helium, neon, and argon in it. And the total pressure is 662 millimeters of mercury. And the temperature is 298 K. All right. We're also given the partial pressures of 2 out of the 3 gases. So the helium is 341, the neon is 112, and then the argon we're not given. So what do you think is the first step here? Go ahead, Chris.
Find the partial pressure of the argon, so you've already got partial pressure of
Yeah, we got to find the partial pressure of the argon. So you know how we're going to do that?
Subtract 12 minus the 2 partial pressures?
Yes. 41 and 112, and whatever's left is the argon pressure. Gives us 209. So that's going to be our partial pressure of argon. So the partial pressure is just atom. All right. So then how do we figure out the ultimate answer, the mass of argon? What do you think is the plan here?
Convert to atmospheres and then plug it into the
Right, so we're going to convert to atmospheres and use the ideal gas equation. And what are we going to solve the ideal gas equation for? For moles, because we've got pressure, volume, and temperature, and then we're going to solve for moles. Because we're being asked about argon, what do we use for our pressure? Component. But it just requires that we kind of keep that straight and make sure that we're calculating the right thing. So we're going to convert 209 to atmosphere. And that comes out to 0.275 atmospheres. Okay, and then it's a simple evaluation of the ideal gas law. In this case, we're going to specifically be looking at argon. Notice that V, R, and T are the same because they're all in the same container, so they have the same volume and temperature, and R is always the gas constant. The thing that's different now is we're using the partial pressure of argon, and we're going to solve for moles of argon, and then ultimately get the mass from there. So we'll plug in that newly converted pressure. And the volume. And then we've got our R. And our temperature, 298 K. Put all that together, and we get 0.0 1, 2, 5. And that's moles of argon. Okay, from there, it's just using the molar mass to convert to grams. And we've got 0.449 grams. Okay, so let's think about what we did there. We found the missing pressure for argon through the law of partial pressures by just subtracting. Then we used the ideal gas equation and came up with moles, and then we could convert moles to grams. All right, everybody good with that so far? Okay. Let's see if we can find one where we deal with this mole fraction issue.
Is the concept always 0.0821?
The concept is always, or yes, the gas constant, depending on units, is always 0.82 or 0.8206, I think it is. You don't have to memorize that. Constants will be given to you.
Yeah, that was going to be my question.
Yeah.
I know there's other constants for other,
Right.
in different units, I guess.
Constants will, in general, in chemistry at least, I don't know about other realms of science, but in chemistry, the constants are always given to you on quizzes and exams. The only one, conversion factors is sometimes what we have to remember, like the metric system, or like the 760 is a helpful one, temperature conversions, but constants are given. So yeah. by the time you're done with all the homework for this chapter, I'm guessing that you'll just know it for now, but yeah, you don't have to remember it. Okay. Oh, that's right. So another issue, because this will come up in the homework too. Something else that we use partial pressure for is when we collect gases over water, or really over anything. But water is where it most often comes up. So if you think about it, we haven't really talked about this, but when you're doing a reaction and you produce a gas, and let's say that gas you want to keep because you want to measure it or you need it for something or whatever, and you want to measure how much you have. Well, once again, you can't really weigh it in a lot of cases. Sometimes you can, sometimes you can't. So there has to be a way of figuring out how much gas you've recovered. And the way that's often done is to collect the gas over water. And what that means is, there's our guy from the other day. That's underwater. Yep, that's different.
He's collecting gas from overwater.
Maybe. That's right, he is, yeah. So here's the kind of a setup. So in this reaction, you are reacting zinc with HCl as you did in lab on Tuesday. No, last week. And what that produces hydrogen gas. You would take an evacuated container, like a beaker or whatever, and invert it into some water. And if it's evacuated, that means that there's no air in it, and so the water is going to push all the way up depending on the atmospheric pressure, just like a barometer. So then as the gas is produced, it bubbles up there and the gas takes up that space. The space that gas is taking up creates a pressure that then pushes down and raises that water level, and then you can measure the pressure of the gas that you've produced. And in producing that gas and in capturing that pressure, now we know how much gas we have. We can convert the pressure to moles and figure that out. The complicating thing here is that water has its own vapor that's mixing with your stuff. Because as we'll talk about in a few chapters, solutions or liquids, even solids often, have a non-zero vapor pressure, which means that they're always creating some vapor. So even when you have a sample of liquid water, there is also water vapor on the top of that water all the time. There's an equilibrium between the vapor and the liquid. It's kind of going back and forth. So that means when you're trying to collect this gas, it's not purely the gas that you want. There's a little bit of water mixed in. And we have to account for that when we do the calculations. So to account for that, we use a table like this that tells us the vapor pressure of water at different temperatures, and then we can use that to subtract it, because the different gases exert their own independent pressures, and so we can say, well, the water vapor is exerting this pressure, so we can just subtract it out from our total pressure, and then that'll work. All right, so here's what a problem like that would look like. So once again, I'm going to type it just to keep it clear here. All right, so here's a photosynthesis test, and you can measure the oxygen gas emitted by an aquatic plant by collecting it over water. So oxygen gas is collected over water at a temperature of 293 K and a total pressure of 755.2 millimeters of mercury. A total of 1.02 liters of gas is collected. How many moles of oxygen is this? Now we should specify oxygen gas here. All right, so we've got that same kind of picture. Oxygen gas, is bubbling up through water at a temperature and a total pressure. Once again, we can write down the things that we know. So we've got is 755.2 millimeters of mercury. So in a normal gas law question, you just convert to atmospheres, plug into the equation, solve for moles. But why doesn't that quite work here? Because water. Yeah, because there's water there. So that 755.2 is a total pressure, not a pressure of the oxygen. So this total pressure is the sum of the oxygen pressure and the water vapor pressure from being collected over water. So if we want to do the gas law, we have to subtract, we have to correct for that so that we're only dealing with the oxygen. So the oxygen pressure is going to be the total pressure minus the water vapor pressure, which in this case is 755.2. And then we would look up the water pressure on a table, and the temperature is, what does it say, 293 K, so that's 20 degrees C. So the vapor pressure from water here is 17.55. And let me make a note here in case you're looking at this later. That's the pressure of water at 20 degrees C. Which is 737.7. Yeah, question.
I was just going to ask, are we going to be given like pressure?
Yes.
Okay.
Yeah.
That was my second question.
Yeah, you don't have to memorize the pressures of water. And if it were collected over some other substance, you could have a different table of vapor pressures of that other substance, and it would be you'd do the same thing. The tricky part about this, so the rest of the problem proceeds just standard gas law, N equals PV over RT, and you plug in your new pressure after you convert to atmospheres and so on. You can complete that for an exercise if you want. The tricky part here is that there's only one indication here that you have to do that correction, and it just says collected over water. So, when you're doing homework or a quiz or an exam, so just keep an eye out for that. That when it says collected over water, or when you're collecting a gas over some other kind of solvent, that you need to correct for that liquid's vapor pressure. You can do that? Great. Okay. All right. So we'll come back to this and do some practice calculations in the second half. Now we want to move into more of the theory behind why all this stuff is happening. And that is called, remember back to the beginning, we talked about the difference between theories and laws. We've just talked about a bunch of gas laws. The Boyle's law, pressure and volume law, volume temperature law, the partial pressures law, all that stuff. Why are those laws? Yeah, they're just reporting directly the observations of what happened. So you change the pressure like this, the volume changes like this. You change the volume like this, the pressure changes like this. It's just literally reporting what's going on there. So then what do you think the kinetic molecular theory of gases is going to attempt to do?
Explain why.
Right, it's going to explain why. So it gives us a theoretical framework that says, if we assume that gases act like this, then we can explain all this observed behavior. So all the observed behavior comes out of the theory, comes out of the explanation for the theory. We have various evidence for supporting that. All right, so the kinetic molecular theory has a few tenets. we're going to talk about the three big math problems and stuff, assumptions. Okay, so here are the three assumptions for the kinetic molecular theory. One is and I think we mentioned this before, but the size of each particle is negligibly small. So the particles have mass, but they don't have volume. Now, of course, that's not exactly true. They do have volume, and we'll see some situations where that becomes important. But we're assuming that the size is negligibly small, and the only thing that takes up space in a sample of gas is the space between the molecules, or the particles, which of course is not quite right, because particles are there and they take up some space. But for the purposes of our explanations, we're going to say, well, they don't. We don't have to worry about the space of the particles. We only have to worry about the distance between particles. All right, second. The average kinetic energy of a particle is proportional to the Kelvin temperature. So the particles are in constant motion. They have no potential energy, essentially. And the Kelvin temperature is proportional to their average kinetic energy. So what's kinetic energy? Anybody remember their physics? What's the equation for kinetic energy? Yeah, it's been a while, right?
Boo physics.
Boo physics. Does anybody know what it depends on? Like what kinds of concepts or what kinds of things? Joules is what kinetic energy is measured in. Yes. So like what is it?
There's height in there?
There's not height in there.
Potential energy.
That's potential energy, yeah. So you got energy is 1/2 mv squared, right? Where m is mass and v is velocity. So why do we care about that in chemistry? Well, it means that as you change the Kelvin temperature, what are you changing about the molecules or the particles? It's energy, and do you change the mass of the particles when you change the temperature? No, so you're only changing the velocity. So that means that we can approximate, or we can talk about the speed of the molecules, the speed the gas particles are moving, is proportional to the Kelvin temperature. We can also say that the mass being in there is important too, because let's say two different gases are going the same speed. Which one has the greater kinetic energy? A heavier one or a lighter one? A heavier one, because there's an M in there. So if you've got two gases going the same speed, but one is heavier, it's going to have a higher kinetic energy and therefore a higher temperature. The reverse of that is, if you have two samples of gas at the same temperature, which one's moving faster, the heavier one or the lighter one? The lighter one, because if they're at the same temperature, that's telling us that the average kinetic energy is the same. So the lighter one must be moving faster because its mass is smaller. Right? So these are all consequences of this idea. Be careful, a little bit careful with this. The temperature is proportional to the kinetic energy, not just the velocity.
Sorry, dear.
As it says right here, the kinetic energy is proportional to the temperature, not the velocity. It's got the mass and the velocity in there, so we have to take mass into account sometimes too when we're looking at different types of gases. Okay. And the third one all collisions are perfectly elastic, which means that no energy is exchanged when gas particles hit each other. There's some sub-assumptions to this, one being that gas particles are always moving in straight lines. They always are just going straight. We already said they're in constant motion because they only have kinetic energy. And whenever they hit another gas molecule or the wall of the container, there's no energy exchanged, because otherwise they would eventually slow down or something. So we're saying they're just always moving around. And one of the consequences of this oops, let me use a different color here. Is that pressure is the result of gas particles colliding with walls. So the reason that fits with that assumption is, okay, if you have a collision, if a gas particle collides with a wall, it exerts a force upon that wall. But since no energy is being transferred, or no energy is being lost, it's only being transferred, that means that the gas particle is also kind of bouncing off that wall with the same amount of energy. So ultimately you're creating you're applying a force to the walls without really like losing energy in the system overall, without losing energy to the surroundings. And so that's creating this thing we call pressure. Okay, so that's the three things. So now let's talk about how we use that to explain the observations that we've already talked about. So let's talk about pressure and volume, what we call Boyle's law. All right, so the law says that they're inversely proportional, that when you decrease the volume, you increase the pressure at constant temperature. Let's word it this way. If volume decreases, the pressure increases. So let's look at what that means in the language of the kinetic molecular theory. What does it mean for volume to decrease at constant temperature when, if we zoom way in and look at the actual molecules or particles themselves? What is happening to the particles if volume decreases but temperature stays the same? Go ahead.
Getting a smaller.
So you're getting a smaller container.
It's going to be hitting the walls more often, so it increases pressure.
Right. So So the key here is constant temperature means, in the language of the kinetic molecular theory, same kinetic energy for the particles, which means the same velocity because they're the same particles. They're not changing mass either. So if things are going the same speed in a smaller space, they're hitting the walls more often. So pressure increasing in the language of the kinetic molecular theory means that there are more collisions with the walls. If we took the tables out of here and we just all start running around at a particular speed, and then the room got smaller, we'd be running into the walls more often. And that's the pressure that we're talking about. So notice how this explains, so in blue, the light blue sentence there, that's just stating an observation. That's the law. That's not explaining why. The explaining why part is saying, well, if the container gets smaller, but all the molecules are moving the same speed, they're colliding with the walls more, and that leads to an increase in pressure. That's the actual explanation for that. So when you see questions like this, especially on quizzes and exams, be careful about what is being asked. So for instance, I might say, explain the relationship or give an explanation for why pressure increases when volume decreases. And the wrong answer is to say, well, it's because of Boyle's law, right? Because that's just stating the same thing over again. It's just saying, well, pressure increases because volume decreases, because pressure increases because volume decreases. You can't just say the same thing over and over again, right? So we want to know a reason, and when we want to know a reason, we look to the theory, and we look to actually what's going on with the molecules or the particles that's causing this particular effect. So let's try another one. Let's try temperature and volume. So as temperature increases at constant volume, at constant pressure, talking about volume now, okay, so who wants to give that one a try? Explaining it in terms of what's happening to the molecules. How do what the molecules are doing explain that? Yeah.
So the molecules are starting to move faster because the temperature is increasing.
Yep.
But since the pressure is constant, that means that they have to be hitting the walls at the same amount. So in order for them to hit the walls the same amount, but still move faster, the walls have to get further apart.
Yep, that works. Did you hear that? Makes sense. So to do these types of explanations, that's exactly what you're trying to do. You think about what these concepts mean in terms of what we just talked about, in terms of how it changes what the molecules are doing, and then you decide how the effect has to, or what has to happen in the second part of the sentence to allow that to be the case, to allow that to be true. Okay, what about the law of partial pressures? So the idea that we can simply add up the pressures of the different gases. How does kinetic molecular theory explain that? Like, it doesn't matter what the gas is or what it's doing. Yeah, go ahead.
I would say that each gas molecule will have its own separate mass, so they would move at each separate speeds.
Right. So, that's right. You want to add to that, Chris?
Pressure's just the measure of how many times things hit the wall. So if you think about it, it's how many times does something hit a wall. So it's just the wall was hit this many times. You can just add them all together, and that should equal the number of times. If that makes any sense.
Yep. Those are both great. Anybody else want to add to it? Yeah, I think you're all right. So because these collisions are elastic, because temperature is proportional to the average kinetic energy, the different particles don't depend on each other. And so the overall pressure is just the collisions, the total collisions. So if the oxygen is making half the collisions and the helium is making half the collisions, then you just add those pressures together and you have all the collisions. There's no other pressure that's being caused by anything else, so we can just add up the contributions of each gas, and that gives us our total overall pressure. All right. So let's look at a couple other consequences of this, or ways that we can think about what's happening in the gases, in the samples of the gases. So one is to think about the velocities with respect to molar mass. All right, so here's a graph of molecular velocity, or relative number of molecules versus velocity, so a histogram. Well, how do you interpret this gas, or this graph? There's a few different things going on. What are some things that we can say about it? Yeah, Chris.
So when there's no gas, there's no collisions, but eventually when you put enough of a molecule in a confined space, there will stop being collisions because they'll probably no longer be a gas.
Yeah, but here we're just looking at a velocity distribution, so we're not really seeing anything about pressure or collisions in this graph. This is telling us about how different samples of gases change their velocity distribution. Yeah.
I'm just taking a guess,
Yeah.
but the lower the molar mass, it seems like the lower the little hill.
Yes, the lower the molar mass, the lower the little hill. So what does that mean?
The greater the velocity, the lower the molar mass, because the lower the weight.
That's part of it. Same thing. Yeah, so if we looked at the average would be the middle, right? Because those are all even or relatively even distributions, so it would be right around the middle. You can see that the smaller gases have a higher average velocity. And that makes sense, because at constant temperature, if it's proportional to kinetic energy, we would expect smaller things to be moving faster, because the kinetic energies should all be the same at a given temperature. But there's something else that's showing here too about this hill thing. Why are the hills different shapes? What is that saying? Yeah.
I mean, the hills having different shapes is just like them having different kind of ranges.
Yeah, exactly. So how does the range depend on molar mass?
It seems like the lighter, or like the lower the molar mass,
Mm-hmm.
the more range they have.
Yep, exactly. The lighter the gas, the greater distribution or range of velocities there is. So if we just look at that green line, which is the lowest one here, that's labeled hydrogen, you can see there's a big range. So there's molecules of hydrogen that have very, very small velocities, and then there's molecules of hydrogen that have very, very great velocities way over here. And the average is right around the middle somewhere. And then we go to helium, we don't have quite as much of a range. We get all the way up to oxygen gas, and the range has condensed even further. And we would expect that pattern to continue for even heavier and heavier and heavier gases. So there's less of a range there, less of a distribution. And we can calculate the average velocity using something called a root mean square technique. And we don't need to get too much into what that is, but it's a type of an average. And it works best when there's a specific type of a distribution, so it works a little bit better than a typical, like a basic arithmetic mean. The equation is this. You don't need to memorize this, but I think it will come up in the homework. And if you want to see the derivation of that, why it works like that, you can actually derive this from the equation for kinetic energy, and that's in your book if you're interested in it. But what it comes out to is that you can determine the average velocity of a gas based on its molar mass, because the average velocity at a given temperature is going to be dependent on the molar mass. The higher the molar mass, the slower the gas is going to go. And then also, or similarly, the velocity distribution changes with temperature. So for the same sample of gas, this is nitrogen, as you increase the temperature, you both increase the average velocity and increase the total range of velocities. All right, a couple other concepts about gases here. Diffusion. This is what we were talking about earlier with the smoking and non-smoking sections. Diffusion just means a movement from, or a movement to equalize concentration. So if you have a greater concentration of a particular gas in one area and less in another area, those will mix. It'll move and mix until it's all even. And what would you expect? Heavier or lighter gases to diffuse faster? Yeah, lighter gases diffuse faster because they're generally more motion going on at the same temperature, and so we would expect that. So, and then that's in fact true. And then there is something kind of related to diffusion called effusion. Effusion is the rate at which a gas escapes through a very small hole. So if you want to see a picture of that. And so how do you expect, whoa. I can't even find the thing here. There it is. All right, I don't know what I did to it, but it's getting pretty angry. Okay, so what do you expect with that? Do you think smaller gases or larger gases, lighter gases or heavier gases would have greater effusion rates?
Lighter.
Yeah, lighter ones have greater effusion rates. And in fact, you can measure this, and the rates are proportional to the inverse of the square root of the molar mass. One thing that you'll sometimes be able to calculate with that, and you'll see this in the homework, but again, you don't need to memorize this equation, is that you can calculate the effusion rates of two different gases based on their molar masses by this equation. Because of the inverse in that first equation, that's why it ends up being flipped. So you'll notice that the rate A divided by rate B is the square root of the molar mass of B divided by the square root of the molar mass of A. These are equations that you'd be given on quizzes or exams, and they're just literally like plug and play equations. They're not, there's nothing you need to be able to do with them except fill in the information and solve it. Good so far? Okay. All right, so now we talked about all these assumptions and ideal gases and things. So we're going to end with talking about real gases. So what do you think the difference is between an ideal gas and a real gas? Or what do you think is the consequence of a real gas? Like why real gases? Do we get
Real gases aren't always pure.
They can be, but even if they're pure, they're real. And what do real things do that ideal things don't? They happen.
They don't always act in the way that we predict they would.
Yeah, they don't always act in the way that we predict they would. So we can go through all this stuff about how the perfect gas should behave given all these constraints. And then we go and measure our actual gases and we find maybe they don't quite behave like that. All right? And so we're going to talk specifically about some things that real gases, or some situations where real gases really don't behave the same as ideal gases. There's basically two things that we're going to look at. two ways in which real gases violate the assumptions we made before. So one assumption we made before is that gases have no size, they have no volume, that only the space matters and the actual size of the gas molecules don't matter. Turns out that's not true. Real gas molecules do have volume. The second is intermolecular forces. We made the assumption that every collision is perfectly elastic, which means there's no attractive or repulsive forces going on. Particularly attractive forces is what we're interested in. But we also know real molecules attract each other. We'll talk about the attractive forces of molecules in a few chapters. But real molecules attract each other through intermolecular forces. So this idea that there's this perfect elastic collision is not quite true. Now the good news is the ideal gas law still works for most kind of practical situations. It's when we get to more extremes that they start to break down. So let's take a look at these individually and look at kind of where those problems are. So just to give you a sense of the size of these problems, here's a graph of, remember we talked about molar volume on Monday. How much volume does a mole of gas take up? And we said, well, every gas at STP takes up exactly 22.41 liters of space. But if you actually measure real gases, pure real gases, at STP, you get some variation. So you see chlorine gas takes up a bit less space. Hydrogen gas takes up a tiny bit more space. Depending on the number of significant figures that you care about, whatever you're doing, the level of precision, this may or may not be a significant effect. So the effect of the volume, where do you think that usually causes problems? At really low pressures or at really high pressures? You go with high pressures? Yeah, why? Why does the size of the molecules matter more at really high pressures and not so much at really low pressures?
Because there's less space between molecules.
Right, exactly. At really low pressures, there's so much space between the molecules that the fraction of the space that the molecules actually take up is not great. But at really high pressures, you're compressing all that, and so the space the molecules takes up becomes more important. So our first one is that at high pressures, the volume is higher than predicted because of the extra space taken up by the molecules. We assumed, remember, everything else was based on the assumption that the molecules don't take up any space. But at really high pressures, they are starting to take up a significant amount of space. And so that's changing, we're assuming the volume is based on just the empty space, and then there's this extra volume that's taken up by the particles themselves that we didn't really account for. So if you're going to graph that for something like argon, if you want to look at what that looks like, you can see that at really high pressures, argon starts to take up a little bit more space than what's predicted by the ideal gas law. But you look at that graph and you look at the size of those pressures, I mean, that's atmospheres, right? One atmosphere, our STP, is like there. So you really don't start to get significant changes to the molar volume for argon until you've gotten to really, really high pressures. Really, really high pressures. All right, so the second one is this idea of forces. So the effect of intermolecular forces has more to do with temperature. Intermolecular forces are molecules attracting each other. Do you think that has a bigger effect at lower temperature or at higher temperature? You're going higher? Why?
At lower temperatures, like as you, if we're talking about like as you approach zero, there's less movement, so there would, I guess if you're at 0 Kelvin, the only things that would be affecting them would be their molecular forces versus that, so maybe it is not.
Yeah, you got to you were started wrong, but then when you started to think about it, you got to the right place. Yeah, at really low temperatures, what's happening to the molecules? They slow down, right? They don't quite stop, but they get slower and slower and slower. As they get slower, the fact that they attract each other a little bit becomes more important. Because when they're moving fast, there's so much motion going on that these like small attractions are only for such tiny fractions of seconds that they don't matter. But as things slow down, that like going close to another molecule or whatever is going to start to have an effect. So because they are attracting each other, what effect do you think that has on the pressure? If the molecules are attracting each other more than we predicted, is that going to increase or decrease the pressure? I didn't hear what you said.
Decrease.
Yeah, why decrease?
Because they're attracted to themselves versus like continuing to
Yeah.
move in a straight line.
Right. So the pressure is collisions. If the molecules are getting attracted to each other, then that means they're colliding less than we would expect. They're not making that perfect line straight for the wall. They're kind of getting diverted and hanging out with some other molecules before making their way over there. So we can say that at low temperatures, pressure is lower than expected because of intermolecular attractions. The molecules are attracting each other, lower than expected pressure. So there is an equation called the van der Waals equation that accounts for all this. And it looks like this. You don't have to memorize this one either. But it's basically our ideal gas law, PV equals nRT. But the P is corrected based on this factor A, which takes into account some of these ideas. And the volume is corrected by this factor B. Now, A and B are not something that you can figure out from just knowing what gas it is. It's something that you have to measure. So you can take a sample of an actual gas, a pure sample of a gas. You can measure it at different pressures, and you can measure, the different things, and then figure out the differences and figure out what these factors would be. If you want to take a look at the factors, like here are some of those constants. So depending on which gas you have, you either have you can get A and B, plug them into that equation, and now you have a corrected gas law for real gases. And there are some predictable things going on here, but a lot of it just really depends on the gas and a lot of other things that are going on. So here is the ratio between PV and RT, which should be 1 for 1 mole of gas, right? For an ideal gas. And then you see some of the other real gases and how they change based on pressure. So at lower pressure, they approach ideality, and then they kind of do some weird different swings. Some of them decrease from ideality quite linearly. Others, it's kind of more weird, and it just varies from gas to gas. So the important thing that I want you to be able to do with real gases is, you can plug in the A's and B's in the equation. I'm not really worried about that. I think there's a homework problem that has you do that. But more interestingly, I think, is explaining what we just went through. So how can you explain what happens to the gases at these extremes and how these deviations from ideality manifest themselves in real measurements. You can do that? Maybe. We'll get there. Okay, let's try some practice problems, and then we'll take a break before we head into the next chapters. All right, so thinking about our kinetic molecular theory, I'm going to pull up another chart here. I think they have these from... Okay, here are two gases. The relative velocities are graphed here. Which of these molecules do you think should have the highest molar mass? Which of those is the heaviest one? A is, yeah. And how do you know? Right, it has the two reasons. One is that it has the smallest range. What's the other one?
The lowest molecular velocity.
Yeah, the lowest average velocity. So the smallest range and the lowest average velocity. Okay, this next graph shows the same gas at two different temperatures. Which is the higher temperature, T1 or T2? T2? T1? Two? Okay, got a couple twos. Yes, it's T2. How do you know?
It's got a higher average velocity.
Higher average velocity and greater range of velocities. This one can be a little bit tricky because the T1 is the taller peak. So if you're not reading the graph right, you could go, oh, it's taller, so that means that has the higher velocity. But that's not right. Velocity is on the x-axis. So the higher velocity is going to be the one whose average is more over to the right. Okay, let's look at some other ones. Okay, I'll type this one out for you. When an airbag inflates, like in a car, does everybody know the chemical reaction that happens in there? It's sodium azide. I'll tell you what that is in a second. Decomposes to sodium metal and nitrogen gas. How much sodium azide is needed, and we'll say in grams, to inflate the airbag to a volume of 11.8 liters. And we'll assume STP conditions. All right, so let me give you the formula here. Sodium azide is N3 minus 1. So sodium azide is NaN3. See if you can figure the rest of this out. Work together if you want. You need to inflate the airbag to 11.8 liters. You will need to write a balanced equation here and figure out how much gas is being produced. stuff, but first ask each other to figure it out. Yeah. All right, so I'm going to give you the equation here. Just make sure that everybody's got that so far. Should be something like this. Oops. Is that what you got for the equation? All right, so then if we're inflating the airbag to a volume of 11.8 liters, oops, I didn't realize I spilled an extra space in there. What is inflating the airbag to those 11.8 liters? Nitrogen gas, yeah. So all of this is what we're assuming is taking up that 11.8 liters. Since we're at STP, we can use the molar volume to figure out how many moles that is. You can also use the gas law equation for that. You can just plug it in and plug in the conditions and solve for n. The molar volume, if you know it, makes things a little bit easier because it saves you all of that business. But you can do it with the gas law too. And now that we have moles of nitrogen, we can just do our regular stoichiometry type calculations to get back to the mass of sodium azide that we need. So what did you come up with for the mass of sodium azide? Grams. 122.8? Or 22.8. Is that what other people got to? Haven't quite gotten there yet? Yeah? So we'll write it out here. What's the mass of sodium azide? Somebody calculate that? The molar mass? It was 22.8? The answer. Okay, great. All right, here's another one. Shouldn't take quite that long, but is a little bit trickier. Ammonium nitrate decomposes forming nitrogen gas, oxygen gas, and water vapor. If 1.55 kilograms decomposes, what is the partial pressure of each gas in the product? Oh, assume. Hold on, I need to give you a temperature and a volume or a. So I will give you a little bit of a hint here. It is not a big, difficult stoichiometry calculation. In fact, you should be able to solve this without doing any stoichiometry type stuff. You still need a balanced equation, but there is another kind of sneaky way to figure this out. You can also do it by a normal stoichiometry type method. That's fine. But there is another way to do it where you don't have to do that. Figure it out? No?
I'm still trying to balance the
Yeah,
equation.
okay, go for it. No. Right, it's just the mole fractions of these. This is STP.
Not the reactants or products.
Right, because the reactants are gone, because the
Okay.
reaction is done, and it's not a
Oh,
gas
okay.
also.
Okay,
Here.
so then just add these up and put them together.
Right, and then you multiply that by the total pressure.
Oh.
I'm going to give you the equation for this one also, in case you got that wrong, if I can find. Did I leave my little pen around somewhere? Does anybody see a little? I can't remember if I was like. Okay, maybe I'm not gonna. I mean, it's got to be here somewhere, right?
Time for a break.
Yeah, maybe. It's not in the computer. Oh, you know what? It's probably in the book here. Yep, it's in the book. I'm marking my place. All right. So we got ammonium nitrate. Of course, everybody knows all your polyatomic ions now, so that was easy to write down. Solid ammonium nitrate decomposes, so you've got nitrogen gas, oxygen gas, and water vapor. All right, to balance this, we need to do that, and then this, and then 2 in front of the nitrogen. Okay. All right, so one way to do this, as I said, is you figure out how much ammonium nitrate you have, and then you figure out the moles of each nitrogen, oxygen, and water, and then you plug them in the ideal gas law, and you get partial pressures for each one. That is one way to do it, and you should get the right answer from doing that. But there is an easier way. Can anybody find the easier way? Yeah.
Is that what I did?
Yes.
I just, when you balance the equation, you then have the moles, so I did, the moles for each of the products over the total number of moles, and then you said times it by pressure.
Right. So you can use this idea that the partial pressure of some given gas, like let's say nitrogen, is the total pressure times the mole fraction. And the mole fraction can be calculated by the equation, because the equation gives you the moles of each one, so you can find the molar ratios that way. What about the total pressure? How do you find the total pressure here? Right. So it's just 1 atmosphere total pressure. So that means that we can calculate the individual mole fractions pretty simply. So the mole fraction of N2 is going to be 2 moles of nitrogen divided by 7 total moles of gas, because the nitrogen, oxygen, and water are all gases. So we've got 7 total moles of gas there. Mole fraction of oxygen is 1/7, and the mole fraction of water is 4/7. Okay. And since it's 1 atmosphere total, that means that those end up being the total pressures too. So the partial pressure of nitrogen equals, okay, let's use our normal decimal places with significant figures and whatever, although it is actually a rational result in this case. 286. Right, and that should add to 1. So did anybody do it the normal stoichiometry way? Where you actually use the gas law to calculate all the partial pressures? Okay, you should have gotten the right thing. I just wanted to confirm that. You should have gotten the same thing. All right, great. Let's stop there. We'll take a break. That's about halfway. And then we will talk about heat and quantum mechanics. Yeah. Okay, well, we could do homework questions too. Are they like ones that you think everybody would want to hear? Okay, I'll take a look at it.
I also thought of an argument for the FE question on the quiz.
The FE question?
So remember how it's supposed to be FE 2+? Does everyone put FE?
Oh, yes.
So in that question,
Yes.
the arrow only goes one way. So
Yes.
while that equation may go both ways,
Yes.
there can only be oxidation in that type. It can only be going in one direction, only one thing oxidizing or reducing, because the arrow is only going one way.
Okay, that makes sense.
So, ready? Ooh, that's a good argument. That's a good argument.
Oh, that was a good quiz.
That's a quiz question.
They also just asked for the element, not the element and its charge, so I just wrote the element.
Okay. Yeah, sure.
Yeah, take all the points I
Because
can
when I
get.
think of the element, I assume that the charge is part of the element.
Okay.
Like that's insinuated.
Okay.
So, yeah.
So what?
I don't know what I'm doing wrong here, but I'm typing in 3 halves times the constant times September, and I'm not getting 32.
Oh, that's because you need a different gas. Oh, you already did that gas. Maybe that's.
Because I understand that then it's the same for all of them, but I don't know what I'm trying to look at.
Oh, okay, wait, go back.
Because I just had to request theirs and both of them to be honest. I typed in for all of them because I need it to be the same, but I can't get that.
Well, you look so nice.
Because it's not even like a rounding thing. This is
Right,
not
right, that's
rounding
what I'm saying.
32.
Yeah.
It's kind of close, but
Yeah.
it's not that. And I checked the book for the constant. Yeah, see right here, and it has the correct, like I want the
Yeah, because that's the joules per mole Kelvin.
And so that should be,
Something weird's happening, like your calculator's set up with some weird setting or something. So I was just gonna check it in my.
should it be
Simple.
radians instead of degrees? That's for graphing.
I get 3240.
What is going on?
I hope that's not like the calculator, because I'm in a math class too, and I need my calculator set a certain way for math.
Try doing it.
Should I do like 1.5?
What if you do it with,
Wait, let me see, let me do it.
instead of the parentheses, what if you do it just like with the multiplication sign? 1.5 times 260.
This is,
Oh, it's 8.314, not 8.134.
so that's just me.
So that's the problem. Yeah, I didn't see that.
Also, why is it 3 halves instead of 1 half? How do you know when to use all of these different ridiculous equations?
It depends
Oh,
on
you
if
have
it's.
to memorize
No,
it?
you don't have to memorize the equations. It depends on whether you're, or what you're calculating with it, and whether you have mass and velocity or not. The point of this rearrangement is so that you can do it with only knowing the temperature rather than the velocity. So if you look at the, I don't know if they do that specific derivation or not. Oh yeah, they do, okay. Oh, no, they actually, okay, so
Because
this is
there's,
why.
there's this kinetic average and then there's this kinetic average.
The 3 halves hour proportionality constant comes from a derivation that is beyond the scope of this textbook.
why to use this as opposed to this, because I tried this originally and it said you don't need to include the molecules in your answer. So like how do I
Yes,
decide?
so
Is it just
the-
based on the units that I have? If it's
Yes.
joules per molecule, then I use this one, whereas it's joules per mole, so I use this one.
you should be able to do this the same way, I believe, but you have to basically calculate, so you calculated the
Right, because
RMS
we did that for
first.
the first part of it.
Okay, so if you have that,
Mhm.
then you have the square root of u squared.
Yeah.
So if you want u squared, if you want that average, then you square that, get this.
Mhm.
Alright, so then you can, or you should be able to still go through this and make it work, but the problem is the m thing, the mass.
Yeah.
I'm not sure that quite works that way, because you have to have the mass then in kilograms, because joules is kilogram meter squared per second squared.
Okay.
So I think you can still do it that way if you want to, but the derivation here just makes it easier.
Okay.
Because then you can use the Kelvin temperature and do that way instead.
Would there be any way that you could maybe make some sort of like study guide, something that you can like fill out and like really, really, really focus on? Instead of like looking at literally all of my notes and just kind of going over it, like I really like to like kind of narrow in my focus and like know what I really need to focus on.
Well, I mean, the problem is there's a lot of stuff. So like, I think if you do lots of different kinds of problems, that's the best way to do that. Because that's what you'll see is lots of different kinds of problems primarily. If you want to make yourself some study notes of the more conceptual stuff, where it's like, like ideas about the kind of molecular theory, that kind of thing, I think that makes sense. But otherwise, it's really more about like being able to look at these types of problems and solve them.
Okay, has you been mentioning a lot of different formulas? I know kind of the standard one is the PV equals nRT, and then different variations of that, depending on what you're solving. But which ones do we not need to know? I remember you were saying the root
Yeah,
mean
you
square
don't need to know
velocity.
the root mean square velocity. You don't need to know the diffusion. You don't need to know the that kind of energy equation that we were just. I mean, you need to be able to use them, but not memorize them.
Well, if you
The
receive
Van
the
der Waals
equation.
equation for the real gases. You need to know that one. Yeah, most of the other stuff comes from the gas law.
I know, I feel like it all just comes from PV equals nRT and then the partial.
As long as you're good with the algebra of like rearranging that,
Mhm.
that should take care of it. And then the partial pressures law, which is just adding up the pressures.
Yeah. Cool. That's one more question. So I got to the answer of this one, but it took a few tries. So I learned this equation, the rate A over rate B equals the square root of the inverse. If you type that in, you get 7. So what you have to do is rate B over rate A equals the square root of rate B over molar B over molar A, and then you get 160, which is the molar mass of Br2. So why is it B over A, B over A, as opposed to A over B, B over A?
Alright, so let's see. So xenon is 75.
So you said
Wait.
it's not B over A, it's A over B.
Xenon takes 75 seconds. And unknown gas takes 83 seconds. So you're saying the unknown is A and the unknown is B, right?
Yeah. So then I put the known A on the bottom. This.
Yeah, but you got that.
That doesn't work out.
You got that switched. That's why, because the way you set this up was, oh, I see, it's
This
switched
was-
later.
yeah,
So
yeah,
this
this-
is A,
Yeah,
and
and
this
then
is B, and then this,
this is
and then
B and this is A, yeah. So that's setting it up like this, but that gives you about 107. Whereas if you do Just cause that's what the formula, it said it's inverse and square root of,
But
inverse.
so it's just not inverse, it's just normal. That's how you got to the answer by just doing it
Normal,
no
even,
inverse?
yeah, even though the law says it should be the inverse square root.
What was it,
Cause this is what it says it should be, so I solved it like that. There's the rate of A, 75, xenon A, so I put the mass of xenon on the bottom, so A to A, and then B to the unknown, gives you about 107, which none of those are 107. But if you do B over A and B over A, you get 160. Bromine is 79, there's two of them, which gives you
Wait,
about 60.
So, how'd you get this over this? So,
Because-
yeah. And then you said, how did you get from that to the unknown, that being unknown?
Because you don't know the mass, so,
But you know the mass of this, is that just the mole? Oh, yeah.
That's
Oh,
what
my
you
God,
know,
okay,
yeah.
another mass, yeah.
Yep. So that was confusing, because I tried to follow the equation and it just does not. It gives you 107 and none of those are equal to 107, but if
Right.
you do the B over A equals B over A, then you get to 160 or 158, whatever it is with sig figs and two bromines is
That works.
160 and that's the correct answer.
That is weird. I don't-
Yeah, this homework was really putting me through this one. I still keep learning.
Yeah, I think some of those are off the net. These numbers switched.
Yeah, because if those were just the opposite, then it would make sense with the regular equation that you're normally doing.
How do you manage this thing?
Yeah, yeah. Here's the problem. So that's supposed to be this one. It's supposed to be 37.
Oh.
Well, no, I guess they just changed it. They changed it, and they changed it wrong, I think. This answer would be different.
Yes,
This
it would.
be one of those.
And that you should do the regular inverse, regular inverse, whatever. Because yeah, this one only works if you do B over A and B over A.
What
Yeah.
number is that, Amy?
That's weird.
25.
Well, maybe mine will be different.
That one you yours is right.
I think I can take that one off the homework.